Okay, so this is where I left off last time, contrasting classical to quantum theory. Now, we were talking about the subshells. We were talking about how each energy level has a certain specific amount of energy the electron must obtain in order to move to the next one or to go down the next level. And the way we see it is spectroscopy, which is why we spend a little bit more time on it than some of the other labs that we do, because you need to have a good understanding that we figured all of this out by looking at the light emitted by excited electrons. And so we use a spectroscope. It is the foundation of our quantum theory. And when we think about it, the transformation represents a change of energy. Remember, we talked about everything goes back to energy and matter. It always goes back to it's interconnected. Okay? And so we're changing energy from electrical energy or heat into light. The color of energy of the light depends upon the change or the changes of energy levels made by the electrons. And so when they jump from the outer to the energy levels, we can see those with the characteristic lines observed by the different elements in the spectroscope. And you've already been playing with this a little bit, so you already have a good understanding of what these lines look like. Every single element has a fingerprint. Every single one of them. So we can identify what we have by the spectroscope. Okay? Because each element has a fingerprint mark when it comes to energy levels. And so this translates into something called S, P, D, and F. And it sounds like a foreign language to you, but it'll make a whole lot of sense in a second. And so beforehand, we did this to try to get acquainted with the periodic table. We marked it up with the charges, with the electrons in the outside shell, all that information. Now you need a second periodic table, because now we're going to designate the S, P, D, and F. And so, when you get it out this time, we're going to mark it up like this. S block are the first two rows and helium. Notice I put a block here for helium to remind myself helium is in the S block. S level have the lowest level energy. Then the second block that we will run through, if we were going from here to here, 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 is this orange block. That's our P block. Okay? And I call our P block basically dumbbells. Okay? And I'll explain that in a second. S is more spherical. P is more like dumbbells and donuts. And D block is our transition elements. This gets a little weird down here. There's a few little exceptions, and so I won't give you the exceptions or stuff until we get a little bit more confident with what we're doing. So this is our D block. I call them double dumbbells or dumbbells and donuts. And that's what that is. And then our F block, truly an odd block, is the very bottom block or inner transition metals. So I want you to color up your periodic table like this. You don't have to use pink, blue, whatever. Use whatever colors you have as long as you can read them. Make sure you put at the top S, P, D, F to remind yourself that the S block is the lowest, P block is the second highest after the S block. Then you have the D block, which has more energy than the P block, and then the F block has higher amounts of energy than the SPD. Okay? You're welcome to put that on there. All right. S orbital has the smallest amount of energy, and we call them spherical. They look spherical. Okay? They're the very basic one we have to do with. Then we have the P, D, and F. Okay? So, a few things to go over here before we get going. Remember that the atomic number determines the element. Okay? The atomic number determines the element. If I have atomic number 6, I'm carbon. Okay? If I have atomic number 8, I am oxygen. I don't care how many neutrons I have. All I care about is the protons. Protons determine who I am. Ground state is always neutral. Protons equals electrons. Okay, chemical activity. Atoms that do not have a full octet or a filled outer shell, they're going to combine with others to get that. They want that stability. The ones that have a full octet or a completely filled outer shell are noble gases. They do not want to combine with others because they don't have a need to. Okay? And the way that the other ones get to the status of noble gases is that they share, gain, or lose electrons. And how much they have to share, gain, or lose determines how active they are. And it all comes down to valence electrons. Vocab word. Okay, so let's practice this a little bit. There are 3 rules when it comes to this. Electrons always occupy orbitals of the lowest energy available. There can only be a maximum of only 2 electrons in any given orbital. The spins will be opposite, Pauli's exclusion principle. Electrons are added successively, filling subshells with electrons in specific order based on the increasing energies of the subshells. I'm going to divide this into 2 parts because this is where some people get kind of confused. Okay? So the first thing we're going to do is we're going to write the electron configuration. Then I'll go back and do Aufbau's principle with arrows. Alright, so I went ahead and did a few. Hydrogen. Hydrogen is on row 1, S block, 1N. So it's 1s1. Row 1, S block, 1 electron. Helium. Helium is on row 1, S block, 2N, 1s2. Okay? There is no shorthand for helium. You cannot write helium as a bracket HE. That is false. Okay, let's go to the next side. We have beryllium. Beryllium is here. It is on the second row, S block, 2N. So I always think about where I'm going, and I write that down first. And then I go back and put what I'm supposed to put. Okay, because you always start with your lowest, which is hydrogen. So it's 1s2, 2s2. I'm now at beryllium. And if I look, 2 plus 2 is 4. Beryllium's atomic number is 4. The other way of looking at this, beryllium is on row 2. It has to go through helium to get to beryllium. So I can also write beryllium in shorthand as bracket HE 2s2 because HE's configuration was 1s2. When I write bracket HE, I am essentially writing 1s2. Doesn't seem like an impressive thing right now, but later on, when we get to fill in a whole bunch of them, you're going to be like, oh my gosh, I love shorthand. Okay? But you must understand how I got there. Carbon. Carbon is in the S block. Is in the P block. It's 2N on the P block. Row 2, P block 1, 2, 2, P, 2. But I had to go through 1s2, 2s2 to get to 2p2 because I always started hydrogen. Okay? 2 plus 2 plus 2 is 6. Carbon's atomic number is 6. Helium. I can write helium, then 2s2, 2p6, because that takes care of the first row. Fluorine. Fluorine is here. It's in group 7. I'm fixing to show you something else too now. 1s2, 2s2, 2p5. 1, 2, 3, 4, 5. Now, if I look only at the second row, 2 plus 5 is 7. Fluorine is in group 7. It has to have 7 valence electrons in the outside shell. Okay? Shorthand once again is helium. 2s2, 2p5. This is right because 2 plus 5 is 7. Plus 2 is 9. Fluorine's atomic number is 9. Last one I'm going to do is neon. Neon is on the second row. It is the noble gas that's on the second row. So it's going to be filled. 1s2, 2s2, 2p6. 1, 2, 3, 4, 5, 6 is where the 6 is coming from. 2 plus 2 plus 6 is 10. I know I've done this right. Okay? Shorthand will be helium, 2s2, 2p6. It will not be bracket neon. So, exponents add up to the atomic number or the number of electrons. I'm going to ask you to skip transition elements until the next video. Okay? Have a great day.